Log on, tune in, find out. Another good idea from Cambridge.
Good morning and welcome on behalf of the organizers, to whom I would like to thank for inviting me and all of us. And these are the organizers were Frank Barth, Edith Deneur, and Christopher Stellitz. Thank you. And without further ado, because it's already late, I would like to introduce Professor Gil Kalai from the Hebrew University in Jerusalem and Yale University. We'll talk about threshold behavior.
Okay, thanks a lot. It's great to be here, and thanks for the organizers for inviting me, both the workshop organizer and the semester organizer. And the microphone is not for you. I think it's mainly for the board.
You are not supposed to hear it.
Yeah, so you're supposed to hear me naturally, but the microphone will not help. So I'll talk about what?
Is it switched on?
It is switched on, yes. It should help at the back of the room. Does it help you, Keith?
Yes.
Okay, so I'll talk about threshold behavior of Boolean and different type of functions. And we will start. So I'll mention a few results and few problems, and I'll try to make it very easy going. And if you have questions, please interrupt me. And we start with, so suppose we have a function f from 0, 1 to the n, to 0, 1, which is a monotone Boolean function. So by monotone, I mean that if y1 up to yn is greater or equal than x1 up to xn, then f of y1 up to yn is greater or equal to f of x1 up to xn. So, and now we look at a measure mu p. This is a measure over all vectors of Lex n, and mu p of the vector x1 up to xn is simply p to the sum xi, I from 1 to n, 1 minus p to the power n minus sum of xi, I from 1 to n. And this is a product probability measure, sort of a Bernoulli measure, and we will denote by mu p of f the sum of mu p x, or let's say sum of f of x mu p of x, x belong to 0, 1 to the n. And we think about it as the measure, the p measure of the function f. And the one thing to observe is that if the function is monotone, then this is a real monotone function. So mu p of f is a function because the value of the f of x is 0 or 1, and this is a probability measure. This is always between 0 and 1, and it is monotone increasing in P. So this is a sort of the setting. So we have this. So one way to think about it is mu P of f. This is the probability that if you choose xi to be 1 with probability p and to be 0 with probability 1 minus p independently at random, then this is the probability that the value of the function will be 1. Okay, and we will be interested in the threshold interval. So since this is a monotone function, there is one we can define. Suppose we take epsilon to be a small number, but suppose it's between 0 and 1/2, and then we can set P1 is defined so that mu P1 of f is equal to epsilon, and P2 is defined so that mu P2 of f is equal to 1 minus epsilon, and we are interested in the threshold interval T epsilon of f. This is the interval P1, P2. So when we draw the graph of the probability that f is 1, so this is the probability that f is 1, and this is the probability that xi is 1, which is p. Then we have a function which starts from 0 and ends with 1, and now it can look like this, and then this will be the threshold interval. Here the value is epsilon, and here the value is 1 minus epsilon. Okay, so this is what we would like to understand, and so let's start with a question. So let's denote by small t, T epsilon of f is just P2 minus P1. So the first question we can ask, we'll make a definition. A sequence Fn has a diminishing threshold interval if T epsilon of Fn tends to 0 for every epsilon greater than 0. So if we have a sequence, if we have a single function, then this probability is some polynomial in P, and usually the interesting thing is to look at families of function and try to understand the asymptotic behavior of this interval. And we say that for a sequence of function, we have diminishing threshold interval if T epsilon of Fn is going to 0. And the question is, so the first question we'll try to understand is to characterize when is this the case? When is it true that this interval goes to 0? Or to identify some parameter of the function f, which the smallest this parameter is, this interval is small. Okay, so here is, so we'll need one more definition, which again, it's fairly basic definition in this study, and this definition of the influence. So ik, so strictly speaking, we don't really need the influence of individual variable for this purpose, but okay, we will need it. So ik with respect to the parameter p, this is the probability that f of x1 up to xn is different than f of x1, x2, and now we take 1 minus xk up to xn. So I hope this is clear. We look at the random, we look at all the vectors, and we compare the value of the function f with the value of the function f, where we leave all the variables as they are, and we switch the case variable. Maybe I should write here xk minus 1 and xk plus 1 just to emphasize that we don't touch the other variables. And this probability is called the influence of the case variable on f, and this depends on this parameter p. And then we have another notion, which is the following. So let's define psi k of f. Psi k of f is the integral of ip of f dp from 0 to 1. So this is the average influence of the case variable over the parameter P of the probability space. And this is called the Shapley-Shubik or Shapley-Shubik value. So here I more or less, it's never called Shapley-Shubik value. It's either called Shapley-Shubik power index or it's called the Shapley value, but let's call it this way. And so this is the average of this influence over all P's. And another way to look at it is the following: psi k of P. This is the probability that. So let's write it. Probability with respect to measure mu bar that f of x1 up to xn is different than f of x1 xk minus 1 minus xk plus 1 up to xn with respect to another measure, not a probability measure, with respect to the so-called equal slice measure mu bar on 0, 1 to the n. And what is the equal slice measure? So the equal slice measure, one way to think about it is first choosing a P uniformly at random. So one way to think about at mu bar is first choose a P between 0 and 1 uniformly at random, and then choose according to mu P. Or another way to think about it, you look at all the 0, 1 vectors, and the slices are the vectors which has k1s, and you give each slice the same probability, 1 over n plus 1, and then you choose in each slice uniformly at random. Okay, so this is the notion of influence and the notion of Shapley value. And now we have now we can ask the question and answer it. The question is, what guarantees diminishing threshold behavior? And the answer is so the sequence Fn has a diminishing threshold behavior if and only if the maximum Shapley value, maximum pk of Fn, so the maximum of k between 1 and n. Okay, I sort of assume that Fn is a function with n variable, and then the limit when n go to infinity is 0. So it turns out that to have for a sequence of a function to have a threshold interval which go to 0 is equivalent to the property that the maximum Shapley value go to 0. So it turns out that the Shapley value is the right parameter to study this global threshold behavior. Okay, so I should mention, so another way to write it is that lim t epsilon of Fn n go to infinity is 0 if and only for every epsilon, if and only if the maximum lim n go to infinity of the maximum psi k of Fn is also 0. Okay, so this is a theorem. So this is so of course this is related to earlier theorem, but this particular theorem I proved I think in 2004. Unfortunately, so qualitatively, it gives a sort of a nice answer, but quantitatively, it's fairly not so good. So let me mention that the quantitative result which comes from the proof is that if the maximum Shapley value ck of f is delta, then this implies that T epsilon of f is less or equal to some constant log 1 over epsilon. So dependence on epsilon is okay, but now we have 1 over log of 1 over delta. So this is the result, and it looks that one of the logs here is an artifact of the proof. So here is a conjecture, and the conjecture says that T epsilon of f is less or equal than a constant log 1 over epsilon 1 over 1 log of 1 over delta. And this is unknown. This would be very nice. Maybe log is a little bit over optimistic, but certainly the log look to be very wasteful. And I should mention that with 1 log, then this conjecture cannot be improved. There is a special case where things are so under a mild symmetry conditions. So under mild symmetry conditions, we can guarantee that all the it is known that the sum of the Shapley values is always 1. So if you have some symmetry condition, for example, if f is invariant under a transitive group, then of course the maximum Shapley value will be 1 over n, and in this case log 1 over log n is the correct answer, and this follows from some old results. So this is a result by Ehud Friedgut and me many years ago, and there it is known that T epsilon of f is less or equal to some constant 1 over log n, or constant log over 1 over epsilon, and this is best possible. And I should mention that there is, let me mention before ending this part of the talk, that there are some results about connecting the symmetry with, so maybe I'll write it another blackboard. So I hope. So there are some results, mainly by Bourgain and me, which relates the type of symmetry to the threshold interval. Now, all these results, once you have symmetry, then there's no need to talk about Shapley value, and it makes much more sense to talk about the original influences. So the question is, so if f is symmetric under a permutation group gamma, then the question is, what can be said about the influence of f as a function of this group gamma? And there are some fairly in some sense, they are close to being sharp results when the group is not overly large. But and then there are some conjectures that I think will be mentioned later. This is a conjecture of Hood and me, which is called the influence entropy conjecture, which gives an even sharper result. And more important, it gives results which may apply to show that the influence is really large. So let me just, I'll just state questions. So questions, find conditions that guarantees one, that the influence of a function is greater than some power of n, alpha greater than 0. So we don't have any general condition. There are some conjectures, but there's no any general condition for a Boolean function which implies that the total influence. Did I define the total influence? Yeah, I should have defined it. The total influence, IP of f, is just the sum of the individual influences. I, K, P of f. And I don't think I defined it. No, I didn't use it, but sum over K, yes. Yes, so a very basic question is to find condition that guarantee that the total influence is greater than a polynomial in n. I don't know, n to the 1/3. We know that the maximum value of the total influence for monotone function behave like square root n. But to find a condition which will guarantee a power law behavior for the total influence is unknown. And also another question is to find the condition that guarantees for IP of f being smaller than n to the beta for beta less than 1/2. So also to find a general condition which will guarantee that the total influence is smaller than a power smaller than square root n is also not known. Okay, so this is the first thing I wanted to discuss. Now the second thing I want to talk about is threshold behavior for a larger alphabet. So
I have a question.
yes.
In this conjecture over there, is it possible that the worst function is symmetric?
Yes. You know, yeah, it is possible. So somehow the question is, so if the function is symmetric, you don't have any strange irregularities. You see, there was the only thing I erased was the picture, which was this. So if the function is symmetric, you don't expect these irregularities inside the threshold interval. So sometimes something like this. And if it's not symmetric, you may have such irregularity. But I don't know of any example where such irregularities really change the conjecture. So it's possible that the best function will be symmetric, and it's possible that the behavior of symmetric function will be the correct behavior also for non-symmetric function. But for non-symmetric function, you can make the threshold interval look more irregular than for symmetric function. So
for tribes, this is tight.
Yeah, so there is a well-known function which is called the tribe function, which go back to work of Ben Or and Lineal. And this function is defined f of x1 up to xn is 1. So this function is very interesting function. You look at all the variables and you divide them to small tribes of size log n, or log n minus log n. And the value of the function is 1 if all the variables in one of the tribes have value 1. And for this case, the threshold behavior is like that one. And another function which is maybe even simpler to think about, although not simpler to analyze, you look at the variables on a circle, and you ask, is the function is 1 if the longest runs of 1 is bigger than log n. So this is another such function, and it also will have equality there. Okay, so the next thing I would like to talk is a joint work with Elchanan Mosel, and this is about threshold behavior for larger alphabets. And you know, I think somehow larger alphabets, so Boolean function, you can think about function from sigma to the n to sigma, where sigma is a finite set, and somehow these functions are a little bit, you can also think about the situation where sigma is not a finite set, like it's S1 or I don't know, SO2 or whatever, some other things. But somehow it looks that going beyond the Boolean case, not so much was done, and it looks that there are very interesting questions for larger alphabets, and often things do not extend in a straightforward way or not at all. So I want just to mention the result we have with Elchanan and say a little bit about the motivation and application. So here we look at a function from sigma n to sigma, where sigma is a larger alphabet, and now we have to think what are the right notions to replace all the notions from the Boolean case. So
can we think of sigma 0, 1, 2? Will it
yeah,
already be?
so let's say this is what I wanted to suggest. Let's think about sigma as 0, 1, 2. So we have only alphabet of size 2. And now we can think about, now we can let mu p1, p2, p3 be a probability measure where the probability of 0 is, the probability of a variable to be 0 is p1, probability of a variable to be 1 is p2, and the probability of value of to be 2 is p3. Of course, p1 plus
P0, P1 and P2.
okay. Okay, P0, P1, and P2, right? Yeah. Okay, I hope I'll be able to make this transformation. What?
Sigma to be 1 to 3.
Yeah, this was my original intention, but okay. So maybe we'll change it here and change it also here to 1 to 3. And, okay, so this is the value of the function when we under this probability measure, and okay, we do need some analog of monotonicity, and although it will be very interesting both in the Boolean and the non-Boolean case to understand sharp threshold behavior when there is no monotonicity. So I'll say a little bit about it, but now let's see what will be the definition of monotonicity. So one definition we can have is the following. Suppose that f of sigma 1, sigma 2 up to sigma n is sigma k. So actually one way to think about the Boolean function and about this more general case, we can think about the Boolean function as a voting rule between 0 and 1. So we have n voters, each one vote for 0 and 1, and then the function tells us about the result, the identity of the winner. And also here we can think about n voters, each one vote for a member of sigma, and the sigma k is the identity of the winner. And so monotonicity can say something like this, that if we have if f of sigma 1 up to sigma n is some sigma, and then we take some element here and change, say, sigma I, and change it to sigma, then f of sigma 1, sigma k minus 1, or let's say that's sigma k, sigma up to sigma n is also sigma.
The alpha is sigma.
Sorry, yeah. Okay, so the analog of monotonicity would be that if we change a variable to sigma, this cannot cause the value of the function to change from sigma to something else. And what do we mean by a sharp threshold? By sharp threshold, what we would like to mean is the following. Actually, now we can draw it. So we have here the simplex of probabilities. So this is this describes P1, P2, and P0, P1, and P2. And now we ask what is the probability. So we can define as before the value, the measure of the function with respect to this probability, P1, P2, and P3. And usually this value will be, we would like to understand when this value is in the interval epsilon and 1 minus epsilon. And to say that there is a sharp threshold behavior means that this will happen only in a very small membrane, I don't know, which may look something like that. So the conclusion we would like to have is that the area of all the triples P1, P2, and P3 for which the value mu P1, P2, P3 of f is belong to epsilon 1 minus epsilon, the area of all this subset of the triangle is very small. And indeed, this is what Elchanan and me managed to show and then to apply for several purposes. And here, so let's call T epsilon of f the area of this membrane. And then we have a theorem which says that if f is invariant under some transitive group of permutations and monotone, then okay, so let's say that T epsilon of f will be this region and little t epsilon of f will be the measure of T epsilon of f. So what we can prove is that T epsilon of f is smaller or equal to something log n divided by log n.
Gil, can you repeat the definition of mu of f? Mu P0, P1, P2 of f?
Yeah, so mu P0, P1, P2 of f is you choose the variables sigma 1 up to sigma n to be, or let's say x1 up to xn.
You take them with that distribution. And
Okay,
then
you choose the variable to be 0 with probability P0, 1 with probability P1, 2 with probability P2, and
Gil, I think there's a little bit of confusion. So the function can take three values, either 0, 1, or 2.
So
And
Yeah.
what you want to say is you want to say that the probability that it's either takes the value 0 with high probability, or it takes the value 1 with high probability, or it takes the value 3 with high probability.
right.
It's not
So
really so what's written is a little
So
yeah, okay.
is
okay.
that number?
Right, okay.
Can I ask, is mu
No.
P01, P2 f a point in the simplex, or is it a number?
Right. So you are right. So you're all right, and this should be
If it's a point in the simplex, you can say that it's not close to any of the
Right, so this-
vertices of the simplex.
yeah. So here we want to be, you're right, not a single probability. It's also some Q0, Q1, Q2. So this is equal to a point in the simplex, and we don't want it. We want it to be.
You want it to be close to any one of the.
We want to be here in this triangle. So.
Right. Okay.
Okay, sorry. So so you say that
So I'm sorry to continue, but do you allow it to be with probability half 0 and with probability half 1? That drawing.
no, I think we want it. So
Just the corners.
Yeah,
Something like that.
something like that.
So you just cut off the. Oh. No. Just the corners, not the. Yeah. Okay.
Yeah. Okay, so this is the correct picture, and this is the result. And the result says that the probability that it will not be in the corner is big of log n divided by log n. And this is true for any finite alphabet. And actually, it took some effort to get it to this shape. It was a power square root log n for quite a long time. But and you need to do some work beyond the Boolean work. And again, one interesting question is the log n necessary?
And if you only want little o of 1, is there any way to deduce it from the Boolean case?
Yeah, so also this result, we use the Boolean case, but I don't know an easy way to deduce it from the Boolean case.
Even if you want a weaker result.
Yeah, even if I want a weaker result. So this is a sort of so it takes some effort. Initially, it looked maybe you can deduce it easily from the Boolean case, but this doesn't work. You need to do some work to use the Boolean case, and if you do it in the best way we still lose for any larger alphabet a log n term. But
question?
yes,
Something about the transitive group thing.
Yeah.
You need it for just small influences, or is there another way you use this assumption?
we need it just for small influence, but one reason to say it this way is that I don't need to define influences.
Okay.
So
Even though you did.
no, I don't need to define influences for the larger alphabet case.
I see.
But yeah, you can define influence for the large alphabet case, and this will carry on. Then you have to assume that there is small influences for every point in the triangle, in this probability triangle, and so on. But if you have a transitive group acting, then everything is working for you. Yeah. So, but you can, as you said, you can get away with a weaker assumption, which does not talk about symmetry. Okay, and I think it's a very interesting question, both in the Boolean case and in the non-Boolean case, to find sharp threshold results when we relax monotonicity much more. It would be interesting to understand conditions even in the Boolean case, which tell you that even the probability go up and down, still the transitions occur only at small places. So it's either very close to 1 or very close to 0 in the entire domain, and there may be several transition intervals. And also here, maybe without monotonicity, but with some relaxed condition, we may have sort of thin membranes which are more interesting geometry, but still they occupy only little O of 1 of the entire area of the triangle.
Did you just claim that if it's non-monotone, it should still be close to 0 and 1 most of the time? Or?
No, it's not true, because if you take the parity function, it's not true. But it's an interesting question. What condition still guarantee that we have sharp threshold even for non-monotone function? Certainly, it's not true for all non-monotone functions. Okay, so I should say the reason we were interested in this result is that it gives some applications which come from equation result about voting rules of Don Saari, and I should say this result is by itself it's not so trivial. So there is a result about the majority rule. So when the alphabet is when we have a alphabet of size 2, then important function is the majority function. And then the analog for larger alphabet is the function is the plurality function. And the plurality function is a much more mysterious. So plurality is the voting rule where with the familiar voting rule where every voter votes for a candidate and the candidate who got the most votes is elected. And the plurality function still has a lot of subtle and mysterious properties which are known for the majority function. One famous conjecture which go back to an old theorem, an old paper by Elchanan and Ryan and Subash and Guy, and one more person. Anyway, is a conjecture that the plurality function is the most stable to noise. This is now a famous theorem for the majority function, but for the plurality function it looks one order of magnitude harder, and it's not known. It's a very exciting conjecture. It has many applications, and the result that we were interested. So there is a very easy result about the majority function, and the easy result about the majority function says that if we have enough voters and we have several candidates, and the decision between every two candidates is based on majority, then we can have any outcome. Now this is very easy theorem, so let me prove it to you. If we have two voters,
What is the statement?
okay, so I'll prove it to you, and then you will see what the statement is. Suppose we have m candidates, and we have one voter which prefer candidate 1 to candidate 2, and so on up to candidate m, and then we have another voter which prefer again m precisely the opposite, but then still prefer 1 over 2. So it has precisely the opposite preferences, but it still prefer 1 over 2 like the first voter. Now if you look at these two voters and you compound the vote, you see that you have ties between any pair of candidates except candidate 1 and 2. This means that by adding such so this can be, say, two family members, and by having such such pairs of voters, you can achieve any relation you want, because here here the average of these two voters is preferring 1 over 2 and ties for all the others, and you can take such pairs for any relation you want to enforce, and this will be the average of all the voters is be any relation you want to achieve. So this is a very easy result for the majority function, and then you can use some probabilistic method to extend it from majority to a function, Boolean function, which has small influences or sharp threshold behavior and so on. And there is a result, similar result for the plurality function, and one consequence of our result is this also extends to general voting rules. But for the plurality function, I don't know a simple proof for it. So the result about the plurality function is that if you have several candidates, so you have a set sigma of candidates, and you have many voters, then you can arrange the preference of these voters so that on any subset of sigma, the plurality rule will give you a prescribed winner and even a prescribed ordering, which can be arbitrary. So this is a nice combinatorial result by Don Saari, and it's still mysterious for me. I don't know sort of such a one-line proof or even a one-page proof about it. So so I see. So there is a result which says that the plurality voting rule can lead to any result you can imagine if you have enough voters. And this is a nice combinatorial result, and I would like to see a nice proof for it. Okay. So now I want to move to another, the last thing I want to talk about, and this is the situation where P is small or where epsilon is small. So these results are relatively easy, and things become much more difficult. So things are more difficult if P is, so we go back to Boolean functions. So f is Boolean again. And things are much more difficult if P is small. So P itself is a function of n, like P is equal to 1 over n to the alpha, e.g. Or if epsilon is small, say epsilon is equal to 1 over, I don't know, e to the power square root n. So if you're interested in this domain, where either you look at a probability product measure mu p, where p is very small, or you are interested in the threshold, not when epsilon is not a constant, but it also starts with a very small probability. Then there are several other behaviors, and the problems became much more difficult. And I want to mention some results, and well, I want to mention one result and one conjecture in this, or I don't know, a bunch of conjecture in this direction. And the result I want to mention, now, why things become more difficult? The reason things become more difficult is the result about the threshold interval become trivial, because there is a famous result. There is a famous result by, for example, if P is small, if P itself goes to 0 with n, there is a famous result by Bolobash and Thomason that T epsilon of f. So if the critical value is P, so which means that mu P of f is 1/2, then T epsilon of f is big O of P. So if P is small, then the result about diminishing threshold behavior are already follows from a more general result by Bolobash and Thomason, which follows from standard some results in extremal set theory, and therefore we have to be much more ambitious. And usually what we want to understand, for example, is the following. We want to understand when is it the case that T epsilon of f is little o of the critical probability of PC of f. And again, PC of f is the value where mu PC of f is 1/2. So this becomes the important question, and see, there are similar things about a small value of epsilon. And again, here it will be more useful not to talk about the threshold interval, but to talk about properties of the total influence. So we want to understand the IP of f. Yes, and so there is a recent result by Khatami. Okay, so before I'll give you Khatami result, I want to mention one thing. One thing I want to mention, there is a reduction. So there is a reduction, which is a very nice reduction, to move from the case where P is small, or from epsilon is small, to the case where P is constant and with epsilon is constant. And the idea is, so we can do, for example, the following trick. Suppose we have f of x1 up to xn, and suppose what we can do is we can replace each variable, so we can look at the new function f of x11 up to x1k, x21 up to x2k, xn1 up to xnk, and we can define this will be f of say x1 up to xn, where xj is xj1 and xj2, so and xjk. So if we take a function and replace each variable by a bunch of variables and define and define it this way, then this allows us to move the critical probability. If here if the critical probability is 1 over 2 to the k, then we more or less move it to 1/2. So this is one easy reduction. And another easy reduction, if we are interested in very small epsilons, we can, again, just duplicate the function. We can look at g x11 up x1k, xn1, xnk. We can take it to be f of x1 up to xk, or f of x11 up to xn1, or f x21 up to x12 up to xn2, and so on. So if we introduce k variables for every one and take all of several independent such functions on different variables, then if here we are dealing with a case where the probability that g, if the probability that f is 1 is epsilon, then by taking this joint, we can push this epsilon again to be bounded away from 0 and 1. So this type of reductions are nice, and they are sometimes useful. They allow, for some type of problems, they allow a very quick way to prove results for general P's using, and I think Nathan Keller had some very nice results about it. But unfortunately, they are not useful enough to understand the situation that we are interested. Okay, so now let me say what is a Khatami result. And Khatami result is sort of a continuation of a work from 1999 by Friedgut, Turot, and by subsequent work by Bourgain. And his result is the following. So if so f is a Boolean function, so this is Khatami. If f is a Boolean function, and suppose that let's assume that mu pc of f is 1/2. Then t. Then if the threshold interval, if t epsilon of f is big O of pc.
An upper bound or a lower bound?
I'm sorry, omega of pc. So if the threshold interval is comparable to the critical probability, then f is epsilon close to a pseudo junta. So there is a fairly there is a very strong reason why. So again, the result by Bolobash and Thomason show that T epsilon of f is always big O of PC. And if the threshold behavior is coarse, this is called a coarse behavior, then the function has a very special structure. It is close to what's called a pseudo junta, and this means that there exists, i.e., there exists a collection, a G of sets of size less or equal to M, so that so the set of junta, let's call it G.
Is the size of the sets or the number of sets?
No, there is a collection G of sets, each of size less or equal to M, so that G is equal to 1 if and only if there exists S in the collection such that xi is 1 for every I belong to S. So we have a collection of sets. It's not a bounded collection of sets. It can be a large collection of sets, a polynomial number of such sets, but the size of each set is m, and the pseudo-junta is a very special function. They have the value 1 if all the variables in one set of the collection have the value 1, and the only reason a function can have a coarse threshold is that it is close to such a pseudo-junta.
So small minterms, right?
Okay, so in the computer science, small minterms.
Is this a monotone F or?
Yeah, this is all monotone. Yeah, I'm not sure. It may be true also for non-monotone.
No, but then what is the epsilon? It's not defined.
Yeah, so if you want it for non-monotone, then you have to talk about the influences rather than the threshold interval. But it may work as well. But let's do it for them. Let's state it for monotone function. So this is the theorem of Khatemi, and an example of such pseudo-junta is the graph property to contain a triangle. So for graphs to contain a triangle, this is an example of a pseudo-junta. So it's not what we call a junta, because what we refer to juntas as the case where we have a bounded size collection, or the value of the function depends on a bounded number of variables. This is not the case here, but this is something quite similar. So, and this is the correct property when the threshold value, when the critical probability is very small. So this is the result of Khatemi, and earlier in 1999, Ehud Friedgut proved a similar result, even slightly stronger, for the case where f is a Boolean function which represents a graph property, or another way to say, or slightly more general, if f is invariant under transitive group of permutation, and if the orbit of this group is if this group have a bounded number of orbits when it acts on sets of size k, then there is under this strong symmetry condition, Ehud proved a similar result, in fact even slightly stronger result. And then there is another result that was proved for any Boolean function by Bourgain, but it was not as strong as this result. It just said that if you have a function with coarse threshold, then it is correlated to something which look somewhat like pseudo-junta, but it's not really described up to a very small error by a pseudo-junta. So this is yes.
Is m exponential in epsilon or worse?
Is m exponential in epsilon?
There are two epsilons here, but
Yeah.
Right. Yeah. Let's call this delta. So what is your question again?
About what's the relation of
To
m
delta.
to epsilon?
To epsilon or to delta?
To delta.
To
What's the relation of delta to epsilon?
it's maybe it's more than exponential. Maybe
More than exponential.
yeah. If I remember correctly, I don't remember. But
Delta is polynomial in epsilon. Yes.
no, you think of
No.
epsilon as 1 over 100 always.
yeah, you can fix delta.
No, fix epsilon.
You can fix epsilon, you can fix delta, and then this m will depend on delta. Okay, so I hope this gives you the picture about this type of a result. And now we want to move one further step and to consider the case where we talk about probabilities. So when this epsilon can also be very small. What happened when this is the last thing I want to say, and I'm really, I don't know, there are various conflicting
Oh, you started
things.
late.
You started late.
Yeah, so I want to say a little bit about the situation where epsilon itself is small. Now, if we really, why are we interested in very, very small probabilities? And the reason is that so far if suppose we want to relate this type of result to classical questions about random graphs or random hypergraphs, then it's still not so useful unless we can talk also about events which are very, very rare. So like we wanted to understand the case where PC is very small, we want to understand also the case where epsilon is very small. Epsilon can be extremely small, something like exponentially small, and we want to understand the threshold behavior there. And it turns out that there is so there are two types of conjecture. One conjecture is quite similar to this result of Khatami. This is some work which I did with Jeff Kahn a few years ago. And there is one conjecture that almost stated like this, except, well, it has several, you have to replace the word pseudo-junta by another pseudo here. Pseudo-junta. And, okay, so this is now, and, okay, so this I should, and then this pseudo-junta says that you don't, not only that you don't insist that the collection is of finite size, you don't even insist that the sets of the collection are of finite size. But you want them to be precisely of the right size, which will account, actually you want them to be the size which is log of this 1 over epsilon. So when epsilon become a parameter itself, which go to 0, then you want to describe a function in terms of a function with small min terms, then the meaning of the word small is now you have to negotiate it again, and then you want to allow these small min terms not to be small in absolute term, but to be small enough that they will account for this small epsilon. So I think I don't have time to formulate the conjecture, which is pity because this is the only obstruction for one of you prove it. So I'll just give you an example, type of a consequence or conjectured consequence of this conjecture, and this is to the relation between the critical probability and another notion which is the expectation critical probability. So this will be the last thing, and I'll just say it in words. So one thing you can do if you teach graph theory, so let's say you teach graph theory and you ask the student, what is the critical probability for matching? So you have a random graph and you ask, what is the probability for the edges that with probability 1/2 you will get a matching? So
Will contain a match.
So the graph will contain a matching. So the most naive way to go about it is to look what is the expected number of matching in a random graph. You make some computation and you see that if the probability of one edge is about 1 over n, or maybe 10 over n, then there is already a huge, the expected number of perfect matching is already very large. Now suddenly this gives you some information. It tells you that the critical probability for matching is at least 1 over n. But if you are very, very naive in random graph theory, you would say, okay, this is it. The answer is 1 over n. And unfortunately, this is not the right answer. So this student, you should, treat him very bad, except that the conjecture of Jeff and me says that this type of expectation computation give you the right answer up to a factor of log n. So you need to be careful, but because sometimes you have to compute expectation not for the graph your interest, but for certain subgraph. But essentially, the conjecture of Jeff and me says that the expectation computation, the threshold a naive student will give you, well, maybe not the most naive, but a moderately naive student will give you with expectation computation differs from the right answer only by a factor of log n. So this is the boldest form of the conjecture, but it turns out that in order to approach such a conjecture, what is needed is analog of this Friedgut, Bourgain, and Khatemi results, which push the theory also for the case where epsilon is very small. So I think I will not say more about that, and I will end here. Thank you very much.
Thank you very much. There were questions before.
So what limits did you get from this version?
Sorry?
So you do get probably some dependency between M and epsilon here.
Here.
Yeah, even if they're not that.
Yeah, for the Khatemi result, definitely. So as I said, I think M is exponential in yeah, you have more than exponential dependence. Both. Okay, so let's forget about this epsilon, because this epsilon is just an artifact of the way I presented this theorem. Usually, these theorems are described in terms of the influence. So they talk about the derivative at one point, and then I think that depends on epsilon is something like log of 1 over epsilon, something like that. So, but the dependence on okay, so there is a dependence on the how omega behave, on the constant here, which is doubly exponential, and there is or exponential in the power, and there is also a dependence on the epsilon or the delta close to a junta, which is also somewhere in the exponent. So it's both in the exponent. I can find, well, maybe you can look at the precise statement in the paper. But the depends on epsilon is not so bad.
Sure. We'll resume at 11:30.